Welcome everybody to Chapter 17, Section 4, Hess's Law, Calculating Heats of Reactions. Here we go. Okay. All right, let me grab a pen and write you a few things. Okay. You know that this is a reaction. And often we know the enthalpy or heat of reaction. Let's just say it's 500 kilojoules. And let's say we'll call this reaction 1, and let's say we have reaction 2. Reaction 2 is different. It's a decomposition, or it could be a single replacement actually, where A can replace B, and so we're going to say that's AC, and now B has been replaced. And let's say the enthalpy of this reaction is negative 200 kilojoules. Okay, now what we can do is, according to Hess's law, we can actually add these reactions, or we could double these reactions. If we double the reactions, we actually double the heat. Let me show you an example of that. Let's say, let's say that we double this reaction. So it would produce 2A, 2 moles of B, and it would produce 2 AB compounds. That means we have to also double the enthalpy of reaction. Okay, so now we have 1,000 kilojoules. Okay, and we can also half a reaction. Let's half reaction B. Okay, let's say we only want to produce half the heat. Actually, this is an endothermic reaction, and so it absorbs the heat. That means we have to multiply the negative 200 times a half. Okay, now let's add them together and see what we get. So when you add them together, because heats of reactions are additive, you have to keep the reactants on one side and you have to separate them from the products. So we're going to end up with 2A and a half an A. We're going to call that 2.5 A. Let's see. Let's write that as a fraction. That would be 4 halves, 5 halves A. I've combined A. Okay. We would have 2 moles of B and a half a mole of BC. That yields, let's see, can we combine anything? No. 2 moles of AB, a half a mole of AC, and a half of mole of B. But the most important thing here is, the thing we're trying to determine is the enthalpy of reaction. And so, since I've run out of room, I'm going to say that would be 1,000 kilojoules now, the summation of the new enthalpy of reaction for this reaction here. I better write it down here. It would now be 1,000 plus negative 100 kilojoules. So that would be 900 kilojoules. And that's an overview of Hess's law. What I'm going to do now is, I don't know what I'm going to do. I'm going to unfreeze this, and I'm going to go back to, let's see, here. I'm going to go back, I'm going to scroll down to an example on why you would use Hess's law. Now, before we do that, I just want to show you something very interesting. It's called a reverse reaction. So let me just show you that before we go on. A reverse reaction is where you reverse the reaction. Okay, if A plus B yields the compound AB and we produce 500 kilojoules, if the enthalpy of reaction is 500 kilojoules, positive 500 kilojoules, we can actually reverse this reaction. And a reverse reaction, or running a reaction in reverse, is exactly that. You switch the reactants and the products. So what I do is I always line up my yield signs as though they are equal signs, and I literally switch the reactants and the products. Now, if I've switched the reaction, if I'm running it in reverse, then I actually need to reverse the enthalpy of reaction by changing it from an endothermic reaction to an exothermic reaction. Okay? And I'm going to call this equation 1, and I'm going to call this the reverse of equation 1. All right, keep that in mind. Keep that in mind while I go to, I'm not sure what I'm doing here. Hold on. I'm not sure what I'm doing here. Okay. Now I'm going to go back to this, and I'm going to show you, I'm getting a little confused, I hope you are not. All right, here's our first example on how to use Hess's law. Okay. You'll find this in your lesson notes. So this is the reaction that I'm focusing on, and I'm not going to actually do the reaction. I'm just going to calculate the heat of reaction on paper. Okay, so this is the original reaction, and now I'm going to number these other related reactions, reactions 1 and 2. Okay, I'm going to show you how to analyze this. What you do is, once you've labeled your reactions 1 and 2, you decide, why do I need reaction 1 and why do I need reaction 2? And we're going to decide what we're going to do to reaction 1. Now, I definitely need reaction 1 because it's the one of the reactions, one of the two reactions where we start with C. Okay, so I'm going to actually rewrite this reaction, and then I'm going to rewrite the heat of reaction. I'm going to round if you don't mind. Okay, kilojoules. All right, so I'm going to add something to this reaction to make it look like the one I'm trying to solve. Okay, there. So I'm going to use reaction 2. Now, reaction 2, by the way, the reason I'm not going to do this reaction is because it produces CO, which is carbon monoxide. So reaction 2, I notice it starts with carbon monoxide, but actually I want it to produce carbon monoxide. So what I'm going to do is I'm actually going to write this reaction in reverse. So be careful, concentrate. Carbon monoxide plus 1/2 mole of O2. If I reverse it, the reactants become the products, and the product becomes the reactant. Now, don't forget, I'm going to turn on the red marker. Don't forget that if you reverse a reaction, you must also reverse the sign of the enthalpy of reaction. So I'm going to write down a positive 283 kilojoules. Great. Now I'm going to add the 2 and see if I get what I'm trying to solve. So let's see. When I add these two together, I have always separate your reactants from your products with a yield sign. I now have carbon plus O2 plus carbon dioxide yields carbon dioxide plus carbon monoxide plus a half of O2. All right, let's see. Now, I might want to simplify this. In fact, I could have simplified this before I added them together. Whenever you have the same element or compound on both sides, before you add them, you can actually subtract them out. It's kind of like when you have +4 on both sides of an algebra equation. The other thing you can do is whenever you have like terms, you can combine them. And so the oxygens can actually be combined. If you have one O2 on the left side, if you subtract half an O2 from the right side, you actually, and the left side, you end up with a half of an O2. And now I'm going to use my erasing tool, and I'm going to erase, let's see, what did I cancel out? 1 mole of CO2 and 1 mole of CO2 over here. And here, tell you what, I'm going to redo this so that it looks nicer. Okay, so once I've simplified, I end up with a half of O2 and carbon, and I produce carbon monoxide. So I've just added 2 equations or 2 reactions, and now I want to add their heat of reaction. Oh no, what's the number here? It's negative, let's see, add a negative and a positive. Here we go. That would be, I think it's 111 kilojoules. Negative 111 kilojoules. You'll have to write me and tell me if that's right. I think it is, okay? And so now, what was the point of all this? Why did I use Hess's law? Well, for a very important reason. I was trying to solve for this the heat of this reaction right here by using 2 related reactions without actually doing the experiment on paper using Hess's law. I hope you enjoyed the video cast. Goodbye now.